Okay, let's jump right into this explainer. Today, we're going on a bit of a journey, from the very predictable, reliable clockwork of classical physics, straight into the totally bizarre, highly probabilistic realm of quantum mechanics. For centuries, right, our understanding of the universe was governed by these strict deterministic rules. It's the kind of physics that lets you perfectly calculate the trajectory of a cannonball or the exact orbit of a planet. But when scientists finally peered close enough at the absolute fundamental building blocks of reality, well, they realized those comfortable, familiar rules completely unraveled. So today we're going to unpack exactly how that happened, why it matters, and where this massive paradigm shift leaves us right now.
To make sense of all this incredibly dense physics, we've broken this explainer down into 5 distinct stages. First, the classical breakdown, then wave-particle duality, the Schrödinger equation, the uncertainty principle, and finally, the unfinished unification quest. All right, let's start with section 1, the classical breakdown. This is where humanity's old, comfortable physics basically just stopped working. You see, when we look at how our classical understanding fundamentally broke down at the atomic scale, the contrast is just absolutely stark. Classical mechanics relies on deterministic, completely smooth trajectories. Basically, if you know a particle's current position and its velocity, classical physics says you can know its exact future forever. It is a universe of continuous flowing values. But early 20th century experiments, looking at things like the photoelectric effect, revealed that the quantum world operates on an entirely different source code. It is probabilistic, it's discrete, and, well, it's chunky. Energy is transmitted in rigid little packets, or quanta. So instead of a smooth ramp, the universe at this tiny scale actually operates a lot more like a staircase.
Which brings us to section 2, wave-particle duality. This was a bizarre realization that completely shattered all those classical expectations.
So here is the really crucial point. Fundamental entities refuse to be just one thing. In the classical world we're used to, something is either a localized particle, like a billiard ball, or it's a spread-out wave, like ripples on a pond. It absolutely cannot be both. But in quantum mechanics, entities like photons of light or physical electrons display completely different behaviors depending on exactly how we measure them. They aren't just particles, and they aren't just waves. They actually possess the properties of both, and they reveal one face or the other based entirely on your experimental setup. It's wild. Following some earlier evidence that electrons acted like solid, negatively charged particles, a physicist named Louis de Broglie came along in 1924 and just radically flipped the script. He proposed that all matter could actually be considered as standing waves. He suggested that moving particles possess a group velocity that's associated with a wave packet. Suddenly, it wasn't just light that had this split personality. The physical matter making up you, me, and literally the entire universe was fundamentally wave-like.
Now, the ultimate proof of this duality is the famous double-slit experiment. Think about this. If you fire electrons at a barrier with 2 slits, your classical expectation is that the electrons are going to act like microscopic bullets, right? They should just create 2 distinct bands on the detector screen behind the wall. But the quantum reality is shockingly different. When you do not track an individual electron's exact path, it acts like a wave. It passes through both slits simultaneously and interferes with itself to create this complex banded interference pattern. But, and here's the real kicker, the moment you place a detector at the slits to see which one the electron actually went through, the wave behavior collapses, the interference pattern completely disappears, and they act just like bullets again. It is utterly mind-bending.
Moving right along to section 3, the Schrödinger equation. Physicists needed an entirely new math engine to describe this wavy reality.
These fundamental postulates effectively replaced Newton's laws of motion for the atomic realm. They basically dictate that a particle's physical observables and probabilities are entirely locked inside this really complex mathematical construct called a wave function. You literally cannot know exactly where a particle is, but you can calculate its expectation value, meaning the probability of finding it somewhere, by operating on this wave function. And just as Newton's equations tell you exactly where a baseball is going to be in 3 seconds, the time-dependent Schrödinger equation dictates exactly how this probability wave evolves over time.
The canonical commutation relation is essentially the mathematical heartbeat of quantum weirdness. In normal, everyday classical math, 3 times 4 is the exact same as 4 times 3, right? The order just doesn't matter. But here, the math proves that the order of operations absolutely matters in the quantum realm. Multiplying the position operator by the momentum operator is not the same as doing it in reverse. They actually differ by a factor of imaginary I times the reduced Planck's constant. It is a tiny microscopic non-commutative difference, sure, but it's a difference that fundamentally rewrites the entire architecture of the universe.
Let's dive into section 4, the uncertainty principle. This is where we see how that weird, non-commutative math leads directly to the fundamental limits of our knowledge.
Because position and momentum don't commute, they share a special, mutually exclusive mathematical relationship known as a Fourier transform. Introduced by Werner Heisenberg back in 1927, this principle essentially dictates that a wave function that's highly localized in position space, meaning you know exactly where the particle is, must mathematically be made of an incredibly broad superposition of waves in momentum space. In plain terms, the more sharply you know a particle's position, the less you can possibly know about its momentum or speed, and vice versa. You simply cannot sharply know both simultaneously. And listen, this isn't just a limitation of our clunky measuring tools. It is a literal, absolute speed limit on information built into the very fabric of reality.
Now, this inherent, inescapable randomness deeply, deeply frustrated Albert Einstein. He genuinely believed that this probabilistic nature was just a reflection of our own ignorance of some deeper, hidden mechanics. This actually prompted his colleague Wolfgang Pauli to criticize Einstein's stubborn desire for an observer who could just passively measure reality without affecting it. Pauli called it the ideal of the detached observer. Because quantum mechanics insists that the detached observer is a total myth. The very act of measuring a quantum system forces it to take a definite state, which permanently alters it.
Which brings us to our final section, the unfinished unification quest, the ultimate boss battle where quantum mechanics meets gravity.
When we try to put all of our fundamental physics together today, we are left with a massive conceptual cliffhanger. On one hand, we have Einstein's general relativity. This is our perfect theory of gravity and the macroscopic universe. But it requires a continuous, incredibly smooth, flowing spacetime with deterministic trajectories. On the other hand, we have quantum mechanics, our perfect theory of the subatomic world, which strictly demands discrete, chunky, probabilistic quanta ruled by the Heisenberg uncertainty principle. Now, at everyday scales, they just ignore each other. But at the extremes, like right at the crushing center of a black hole or the exact instant of the Big Bang, these two sets of rules are forced to overlap and the math completely breaks down into impossible infinities.
Because of this deep, fundamental incompatibility, physicists are desperately searching for a unifying theory of quantum gravity. They are exploring highly complex mathematical frameworks just to bridge this gap. Some are looking at asymptotic safety, which tries to find a non-trivial fixed point in the math where these completely contradictory coupling constants can safely coexist at high energies without just spiraling into infinity. Others are trying entirely new geometries through string theory or loop quantum gravity. They are all just searching for a consistent framework where gravity finally plays by quantum rules.
And so it's a mystery that leaves us all to wonder. If general relativity perfectly describes the cosmos and quantum mechanics perfectly describes the atom, well, which one will inevitably break to reveal the ultimate source code of the universe? Will space and time turn out to be pixelated and quantized? Or is there a deeper, smoother reality we just haven't grasped yet? This paradigm shift that began over a century ago is absolutely still unfolding today. I really hope this explainer helped you understand the fascinating quantum engine that runs our universe. Thanks for learning with me today.